Hello, everyone. Hello,
Hello.
David.
We've got a fabulous sheet tonight, I have to say.
Has everyone seen the new sheet? Assignment 4?
This is it's wonderful. It's wonderful material. It's a little bit a blast from the past. Certainly in this country, I don't know if things are different elsewhere, but this is, these problems would have just been completely standard in the kind of 1950s and 60s, and before that, but then have really sort of fallen out of school level mathematics. So this is a great sort of walk back through sort of back into history. I mean, I must confess at the outset that I'm not blessed with the best 3D sort of visualization. I think some people are are very lucky that they can sort of see these things much better in their head. So as I go through the sheet, there might be times when I drift away from a sort of purely geometric way of approaching the problems. When I did them earlier, I quite like. Well, I feel more comfortable in a sort of algebraic kind of vector-based approaches using the sort of dot product and cross product and stuff like that. So I hope that's not totally forbidden, Vlad.
No, it's fine. It's fine. Yeah, I mean, these problems tend to be not to be solved by vectors, but I mean, all methods are good, right? Because yeah.
Yeah, I mean,
Absolutely.
all of them can be done in completely classical ways. But just from time to time, the sort of I'll definitely do the problem with the angles in a tetrahedron. And for me, the kind of the simplest intuition is that the centroid of the tetrahedron is just going to be at 1/4 of the, it's just going to be at the center of mass. So it's going to be the same as if you put a point mass on each of the corners, and then you can find the you can find the coordinates of the center of mass of the tetrahedron quite easily, and then just use vectors and dot products. But I think it might be interesting later to actually contrast those two approaches. I mean, I think maybe this is the perspective of someone whose natural tendency is to use vectors, but I'm in admiration of pure geometry. I always think the pure geometry is just more elegant, and if you can do it in a purely geometric way, that sort of feels to me like you're sort of really playing the game. But I think, like a lot of people, I think my underlying algebra is just a little bit more secure than my geometry, partly because of the schooling that I went through, where these sort of questions have sort of fallen off the curriculum a little bit.
Right. Oh, I think we can start, and yeah.
Okay. So for this for this sheet, I think it's very natural just to look at a subset of the problems, because it's very difficult to compose problems. So problem 2, in which diagrams are the cross sections constructed correctly and which are not? So the game here is all of these things are kind of drawn very cleverly in ticks to look like a plane, but some of them we'll see are actually sort of fairly rogue. Now, let's deal with the ones I think which are obviously fine. And E is, I think E is the most instructive one to start with. So why is there absolutely no problem whatsoever with the plane in E? And this is almost kind of axiomatic. So in diagram E, we're simply given 1, 2, 3 points. And as long as 3 points are not collinear, they determine a unique plane. So there is clearly a triangle is clearly a planar shape, you can't draw a triangle that doesn't lie in a plane. Yeah. If you had a three-legged table, it would never wobble. Yeah. You can only wobble when you introduce the fourth leg. That observation that 3 points define a unique plane helps us see some of the ones which have been put in that are a little bit rogue. So if we look at diagram C, this point, and this point, and actually indeed this one, all lie on this front face. So the moment we have, I mean, we've got 4, okay? So that's even worse, right? But the moment we've got 3 points lying on a plane, the unique plane that contains those 3 points, you know, as soon as we've got a plane that contains those three points, that's the only plane that contains those 3 points. So these 3 points in C, which lie on the front face, okay, the plane that contains them must just be the front face. And that means that these 2 points at the back are just wrong. They're just in the wrong place. D is similar. We've got 3 points on this face of the triangle, and so again we can't have a point which lies off it. B, I think B is fairly clear that there's no problem with it. You can clearly do that slice. Is there an axiom which shows that this one is fine? Well, there's 2 parallel lines, and 2 parallel lines define a unique plane. So that shape is planar, that shape is just a rectangle. I must confess that A is the one that I needed the most thought about, but then the sort of penny dropped that this line here through these 2 points lies in this top face. Okay. This line here through the other 2 points clearly meets the top face at a different point, so it doesn't meet on that green line. So what we've got here is we've got a green line and a blue line. Do not intersect. But if, as the diagram suggests, they lie in the plane, then any non-parallel lines intersect. So the only way this could be a plane is if those 2 lines were parallel. Okay. But for them to be parallel, they would need to have the same direction. So for them to be parallel, the green line just lies horizontally. Okay. For the blue line to lie horizontally, the point, the other point on the line would need to also lie on the bottom face. Okay, so the blue line would have had, the 4 points would have had to have been like that blue line for us to lie in a plane, and then it would have been fine. Then it would have just been 2 parallel lines, and it would have just been much more like B. So as a summary, A is wrong, B is fine, C is wrong, D is wrong, and E is fine. Okay, I'm just going to chat in a moment about this question in a moment. If you've got any questions about it, put it into the chat. If not, put a thumbs up. And I'll address any questions that come up in a second. But then we're going to look at I said earlier I wasn't going to make up any questions, but this one is particularly good. So let's take a cube. Okay, so a normal cube. And what I want to imagine you to do is that we're going to put this cube through a sort of salami slicer, and we're going to feed it starting at this corner, and then do parallel cuts until it goes through that far corner. Yeah. So you could imagine hanging the cube from one of its points, and then taking a horizontal slice through the middle. Okay. And my question into the chat is, what would be the resulting shape? What shape would we get if we chopped a cube in half in a plane parallel to the two, in a plane which is perpendicular to the line, the space diagonal, and halfway between the two opposite corners. Right, so someone suggested a triangle, which is a good answer. Okay. What I'm going to do here is, and I said this in the intro, I'm going to do a slightly algebraic approach. So I'm going to call this bottom corner of the cube 0, 0, 0, 0. This corner is 1, 0, 0, 0. This corner I'll call 0, 1, 0. This one 0, 0, 1. This back edge 0, 1, 1. This edge 1, 1, 1. This edge would be 1, 1, 0. Sorry, this vertex. And then this vertex is 1, 0, 1. Okay. So we've got eight vertices of the cube, and the 8 vertices of the cube are kind of like binary. They've just got all choices of zeros and ones. Right, let's take an algebraic approach. Our cut is perpendicular to the line that joins 0, 0, 0 to 1, 1, 1. So the plane is perpendicular to the vector 1, 1, 1. And I will do a purely geometric approach later. So the plane that we want is of the form x, y, z dot 1, 1, 1 is equal to some constant. So we get x plus y plus z is equal to some constant. Now, what is that constant? Well, the constant at the vertex A would be 0. The constant at the vertex B would be 3. So at the midpoint, we would want x plus y plus z to equal 3 over 2. Okay, so what we want to look at now is when this meets each of the different edges. Now, an edge, let's think about the different edges. So this edge here has got the property that the x coordinate is changing and the y coordinate and z coordinate are both equal to 0. Okay, but if y and z are both equal to 0, so if we consider on AB, y equals 0, z equals 0. So the line is just x, and then x is between 0 and 1. So it's that little line segment. But if y equals 0 and z equals 0, it meets the desired plane at x equals 3/2. But that's outside of the line segment AB, because the line segment AB only runs to 1. So this has got no solutions. Exactly the same argument shows that there's no solution on this edge or this edge, because on those 3 edges that point out from A, 2 of the coordinates are 0. And so the third coordinate would have to be bigger than 1 in order to make it equal to 3/2. Right, let's consider this top edge here. So on this top edge, we've got that y varies because we're going into the board. And we've got x equals 0 and z equals 1. And then, so to solve, x plus y plus z is equal to 3/2. With x 0 and z 1, we get that y is equal to 1/2. So our desired plane meets this edge here at the midpoint. Okay. Now, so and its coordinates are 0, 1/2, 1. Now we've got a very big geometrical idea coming up here, okay, which is symmetry. So by symmetry, if one point on the intersection of the plane and the edges of the cube is 0, 1/2, 1, so we have one solution is 0, 1/2, 1. Can anyone suggest in the chat, just by symmetry, other solutions that we're going to get? Okay, and the big idea is symmetry. Okay, so this pink edge that I just shaded is an edge which has got the property of neither being incident with my bottom left front corner, nor incident with my top right back corner. And there are 6 edges like that. Okay, there's 12 edges in total in a cube, and 6 of them neither meet A, B, or C. And by symmetry, we just get the midpoint of each one. So we get the midpoint here, 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 and here. So 1, 2, 3, 4, 5, 6 of them. Okay, and then for completeness, we should consider the 3 edges which are incident with C and convince ourselves that we get no solutions there. So this sort of edge here, the x and the y are both equal to 1, and then the z varies, but because z just varies between 0 and 1, the value of z that would be necessary to make it equal to 3/2 would be -1/2, which would be somewhere down here. So what we can see is this desired plane meets the cube in 6 points. Okay, now, some of you might be blessed with a very good 3D visualization. Others of you might just be blessed with a sort of geometric kind of intuition. What shape would you suggest is formed by those 6 points. Okay, so those 6 points, and this is where it's quite hard to draw, form a regular hexagon. Okay, and I'm just looking at the chat. The people at the beginning, it was a roughly 50-50 split. Some people said triangle. Some people, sorry, quite a lot of people said triangle. Now, we can see what happens. Another sort of geometric way of visualizing this is seeing what happens when we take more slices. So to start with, when we feed our cube into the salami slicer, we do indeed get slices that are just triangles that are bigger and bigger and bigger. But a critical point happens here when we cut through those, when we're cutting through those 3 vertices which are incident with A. Because when we cut further, we start to just bite into a little bit on the purple side. So what we get, as our slices increase, we get bigger equilateral triangles. Then we get an equilateral triangle of length 1 when we meet the 3 vertices which meet A. But then when we get past that, we get an equilateral triangle which would be bigger than 1 because it would want to meet a larger cube, but doesn't. And so we lose a little bite out of each corner. So we get a shape like this. And so to clarify, if this makes it clearer, these 3 yellow bits here are where we're meeting. No, that's not right. We're not meeting the yellow edges at all. We're meeting the purple. We're meeting those purple edges. Okay, but when we just get past the corner, we have an irregular hexagon. But then as we get into the midpoint, we get exactly a regular hexagon. And then when we get to C, it starts to be skewed the other way, and then we get back to a triangle. So the progression is triangles through hexagons, and then eventually back to triangles, and then those triangles get smaller. Okay. There's a very, very famous mathematical book called Flatland, written around the sort of turn of the 20th century, and it's written from the perspective of people that only ever live in a flat universe, and it sort of imagines what their interaction with the 3D world would be like. So if you were in Flatland and you saw something fall through your world, which was a triangle getting bigger, then a hexagon, then a triangle getting smaller, if they had enough like intuition, they might be able to realize that what fell through their world is a three-dimensional cube. And this book, Flatland, was written at around the time when mathematicians were starting to think about 4-dimensional shapes. And 4-dimensional shapes you can think of in the same way. You can just think of 3-dimensional slices through them. Okay, so that's a lovely problem. And I've approached that a little bit in the spirit of the sheet in classical geometry at the end, but then also a little sort of nod to vectors at the beginning. Any questions, comments about that, or give me a thumbs up if you're ready to move on. Good, thumbs up. Did you like that problem? I love that problem. It kind of makes sense when you think about it, that a cube has got 12 edges, And so it's going to meet 3 initially when it's a triangle, 3 finally when it's a triangle again. So what's it meeting in the middle? It must be meeting the remaining 6 edges. Right, I'm going to look now at question number 6. Okay. So it says, for a regular tetrahedron with edge length 1, find the angles the lateral edges make with the base. So let's consider our tetrahedron. Okay, so everything is of length 1. And I've drawn that very badly. Maybe I should have drawn it with a ruler. Okay, but all these edges are of length 1. And I'm sort of here kind of looking down on it. Now, by symmetry, where will the top, above which point will the top of the, above which point will the top of the tetrahedron lie? Okay, so it makes sort of clear sense to me, okay, that the point of, if you project down from D to the base, then the distances to each of the corners will be the same. Okay, so we must be at the circumcenter. The circumcenter of an equilateral triangle. So I'm just going to draw the base ABC. Okay, so that the circumcenter is the point where the perpendicular bisectors meet. Okay, and for an equilateral triangle, that's also the angle bisectors. So this point here, which I'll call G, okay, is the point on the base directly below D. Now, I said at the beginning that in the 1950s, in the 1960s, you know, kids just did tons and tons and tons of geometry. So there was sort of lots of facts that they just knew about circumcenters and centroids and things like that. We maybe don't know these things quite so well, so we need to calculate them a little bit more. So we were given that the length of the equilateral triangle is 1. So this point M is at a distance 1/2. Okay, this angle in here is 30 degrees. So we can say that MG is equal to 1/2 tan of 30. And tan of 30 degrees is 1/√3. So this is 1/2√3, which is √3 over 2 times 3. So that's √3 over 6. I'm just going to find the length MC. Okay, and this length MC I could get from Pythagoras, because I've just got a right angle triangle with length 1 with length 1/2, and I get this. So MC squared is 1 squared minus 1/2 all squared, which is 3/4. So MC is √3 over 2. And I'm really at this point just curious to know how much kind of elementary, like classical geometry, people know. But what general result is this a special case of? Okay, so here, this point G is where all the midpoints meet the opposite corner. And I got that it was √3 over 6. The height of the triangle was √3 over 2. Does anyone know a much more general theorem that this is a special case of? Well, the general theorem is that if you draw any triangle, equilateral or not, and then look at the midpoints of the three sides and join them to the opposite corner, then each of these lines, these three lines, which are called medians, they all meet at a special point, which is called the centroid, and the ratio of each of those medians, the centroid divides it in the ratio 1 to 2, so 1/3. So it's absolutely no coincidence that MG is 1/3 of MC. So this distance here is √3 over 2 over 6. Okay, what we can also do next is we can also find the length AG. So the length AG, we've got a length of 1/2, we've got a length of √3 over 6, and we can find AG by Pythagoras. Okay. Or if we're more clever, okay, we can avoid Pythagoras, okay, and we can just, because Pythagoras would just be a bit nasty. Pythagoras, like we do it normally because, you know, it's familiar. But we could also just note that AG is the other part of the median. So AG is going to be twice √3 over 6. So it's just going to be √3 over 3. Alternatively, we could have just noticed that if this angle is 30, this angle is 60, and then used cosine of 60. Okay, but we've got that AG is now √3 over 3. Okay, I think the section of this sheet that this was in was cherchez the triangle. So what we can now do is we can now get a right triangle with side length AG, and G is special because it's the point exactly beneath D. So we can now draw the triangle AGD. So the triangle AGD looks like this. And AG is √3 over 3. AD is the side length of the regular tetrahedron, so it's just 1. So we can get GD by Pythagoras. So GD squared is equal to 1 squared minus √3 over 3 squared, which is 1/3. So GD is GD squared is 2/3. So GD is square root of 2 over square root of 3. And if we multiply top and bottom by √3, we get that GD is √6 over 3. Okay. Now it asked for the question, remember, we should keep an eye on the question. Asked for the angles that the lateral edges make with the base. So the angle which they want, that's exactly the angle DAG. Yeah, because G is the point which lies beneath D. And so the angle that the lateral edges make with the face is just that alpha. And I guess you could say, well, it's your choice, yeah? We could say that sine alpha is √6/3. We could say that cos alpha is √3/3, or we could say that tan alpha is √2. And so that is that angle. Okay, so we've done the first part, we've done A. Okay, it then says the angles that the lateral faces make with the base. So the lateral faces, we now want to use not the length A. We're now looking at the angle made by DG and then going to the midpoint DM and then this angle in here, I'll call it psi. So the triangle we want there is DGM. Okay, so DGM we know GM from our previous work is √3/6. Look, that's there. We know DG by our previous work is √6/3. And I guess we don't need to find the length MD. We could just say that the angle that we want is, we can just get the tangent. So we do √3/3 over √3/GM √6. Sorry, GD is √6/3, not √3/3. So it's √6/3 over √3/6. So √6/√3 is √2, and then we times top and bottom by 6, so we get 2√2. Right, the last bit of the question says find the inscribed sphere. The radius of the inscribed sphere. Okay, there's a hard and an easy way. Okay. Can anyone think of the easy? Can anyone think of the well, I don't know if it's easy or not. Okay. There's a little piece of knowledge which might be quite useful. And the piece of knowledge is that if you've got a regular tetrahedron, that the center of mass is just the same as if you put a point mass on each of the edges. So if you now consider the height of the center of mass, it's just going to be the sum of the heights, which is the height of D above the base, which is DG, and then divided by the total mass, which is now 4, because there's 4 point masses and only one of them is at that height. So the answer, when we do all our hard work, the sort of physics is going to tell us that the answer is going to be DG/4, which is √6/12. Okay, but I suppose we'd better we better really prove this. Okay, so let's go back to our diagram. Okay, so we've got the point G lying beneath D. We've then got the line joining D to M is along the face. The inscribed sphere is going to be a sphere who, if you just look at it in sort of profile, is going to be touching both faces. So it's going to be touching MD and MG, and that's going to be at the same distance. So these two distances are the inscribed sphere. These two distances are also the same. Okay, and okay, and we know that this angle in here, oops, we know that this angle in here, the tan of it is 2√2. What we can also see is that if we divide this angle in two, we've got phi/2 here. We've then got 90 minus phi/2 here, 90 minus phi/2 there. So this angle here is 180 minus phi. So this angle in here is my complete angle, psi. Okay, there's probably a circle theorem which can do that as well. Right, we know the distance mg. We know that we found the distance mg earlier. We found that mg was √3/6. So we know that this distance mg is the same as this distance, because both of those are the distance to the point of contact of a circle. So this distance here is also √3/6. We can find the total distance MD by Pythagoras. Okay, so we can say that if we look at this triangle, we've got MD, DG, and M. We can say that MD squared is equal to √3/6 all squared. So that's 3/36. So that's 1/12. √6/3 squared. So that's 6/9. So that's 2/3. And then if we make a common denominator, that's 9/12. So MD is the square root of that. So that is 3 times 2 root 2. So that's 3 root 2 over 4. And now we're almost done, because I know the total distance MD. I'll call this point where the circle touches MD P. So I can find PD. Okay, so PD is MD minus root 3 over 6. And that then gives me that this is root 3 over 3. So this distance here is root 3 over 3. But now we've got this right-angled triangle with height root 3 over 3, with angle here psi, and we've now got a right-angled triangle with the in radius. But I know what tan psi is. Tan psi is 2 root 2. So R is just root 3 over 3 divided by 2 root 2. And then if I simplify that, I multiply top and bottom by root 2. So I get root 6 over 12. Okay. But the physics gave me a much nicer way in for that distance being root 6 over 12. Okay, so obviously the angle chasing, the drawing the right angle triangles, is very classical, but a little bit of intuition also goes quite a long way. And the general case for any tetrahedron is that the center of mass is 1/4 of a uniform tetrahedron is 1/4 of the coordinate vectors of A plus B plus C plus D. And here, because the center of mass is going to coincide with the in circle, that just means that it's 1/4 of the way up the line which joins the top vertex to the centroid of the base. Okay, so that's the radius of the inscribed circle of a tetrahedron. Any questions about that? Should MD equal root 3 over 2? Yes, it does. Yes, root 3 over 2. And then that's where we got here, root 3 over 2 minus root 3 over 6 is root 3 over 3. I mean, you get all these similar lengths you get all these sort of similar lengths coming in. If you actually do it, you shouldn't be at all surprised that these two distances are also equal, because the center of the inscribed circle is the same as the center of the inscribed sphere is the same as the center of the circumsphere. Okay, is everyone happy with problem 6, or would anybody like anything to go over? Excellent. What I'll just mention very quickly with question 6 is you can also just do it almost entirely with dot products and vectors, and I personally would find that less. I personally would find that slightly less intense. Okay, let's have a little look at Cavalieri's. Let's have a look at Cavalieri's principle. Okay, really, really beautiful bit of mathematics. So the idea is, let's imagine you've got I always think of it in terms of something like a sort of sausage, some sort of salami. Okay, but let's imagine that it's not a sort of regular sort of cylinder or anything like that. So we've just got some salami sausage. Okay, we can then put this salami sausage through a kind of slicing machine. And at each layer, we get a slice. So let's imagine we slice our salami and we get all of these little slices. If we then take each slice and imagine that the salami is sort of malleable, moldable, reformable. If we then reform each slice to be just a different shape, okay? So we just stretch it, pull it, I don't know, turn it into a square, say. Okay, but of the same area. So the areas at the equivalent height are the same. Then the intuition is that we have not changed the volume. Okay, because we've just remolded each slice, then we restack them up, and because the area is the same at each level, the overall volume of the shape is the same. Okay, the sort of integration-y idea is that the change in volume is equal to the area at the height h times dh, so the cross-sectional area. So dv is equal to the area at height h times dh. So the volume is just the integral of the area at height h between, I don't know, h equals 0 and h equals h max, so the top of the shape. But obviously, the value of the integrand is determined entirely by the area function. So if two shapes have got the same area at each height, they have the same total area. And Cavalieri applied this to a sphere. So if we imagine a sphere, and the sphere has got radius r, then at height x, the cross-section is a circle. Now, what is the area of that circle? Well, it's pi, and I'll call it r squared, where r is the radius of the circle at that level. But now, by Pythagoras, we know that r squared is r squared plus x squared. Okay, and so now little r squared is capital R squared minus x squared. Okay, so the area is pi capital R squared minus pi x squared. Okay, so Cavalieri's next insight was to think, right, how could we do this in a different way? So what we could also imagine is just a cylinder of radius r. Okay. And then at the height x, we could just decide to take away a circle of radius x. But one way to do that is just to have a cone where the radius of the cone is equal to the height. Okay, so the two lateral edges fan out at 45 degrees. So then at each height level, this sort of cut of the cone is pi x squared. So the outside of the cone so this green area, so the green area is just equal to pi r squared minus pi x squared. But by Cavalieri, or the Cavalieri principle, we can have this useful association that the green area of each cross section is the same as the area of the cross section of the semicircle at the same height. So the total green volume, so the green volume outside of the cone, so the volume outside the cone is equal to the volume of the semisphere, of the hemisphere. But the volume outside of the cone is the volume of the cylinder minus the volume of the cone. So we've got pi r squared times r, so that's just a prism, because pi r squared is the area of the sort of base of the prism, and because it's a cylinder, a cylinder is a prism, and the height is r. And then the volume of a cone is 1/3 pi r squared times its height, which is r. So therefore, the volume of the hemisphere is equal to 2/3 pi r cubed, and the volume of a sphere is equal to 4/3 pi r cubed. Okay, there's a slight hole in this proof, or rather there's a bit of this proof that, this proof relies on a result which you might argue we haven't proved. Where is the hole in this proof? Excellent. The hole in this proof is the volume of a cone. So the question is, how do we know the volume? How do we know the volume of a cone? Okay, so the volume of the cone, we think the formula is 1/3 pi r squared h. What is this formula a special case of? Well, a cone is a special type of pyramid. Okay, so the volume of a cone is, so the volume of a cone, the result comes from, the formula is a special case of volume of pyramid. Okay, and the volume of a pyramid is 1/3 base area times height. Ah, very good. And what someone's put into the chat is, I can find the volume of a square-based pyramid okay, because I can clearly fit 6 square-based pyramids into a I can fit 6 square-based pyramids into a cube, yeah, because if I've got a cube, from each of the faces, I can just draw a pyramid that goes down into the midpoint of the cube. Okay. And so that pyramid, which has got side lengths h and h and height h, has got volume 1/6 h cubed, which is the same as 1/3 h squared times h. Now the trick is, the trick is now, how do we go from, we've got one pyramid which satisfies the formula we've got one pyramid which satisfies the formula 1/3 base area times height. So this is the volume of this special pyramid. Okay, and it's a square base pyramid. And it's got height x/2. But what we can do now is a series of manipulations. The first thing we can do is we can note that if we just stretch the cube vertically, okay, so if we just do a vertical enlargement, what that means is that if you think of all the previous, if you slice it into slices, each slice is now twice as thick. And that means that each slice has got twice the volume, so the pyramid has got twice the volume. So we can, if we double the volume, if we double the height, we double the volume. So the volume is just proportional to h. So if we can now stretch our square base pyramid with height x/2 and just get it to any height. But now what we can do is we can now draw any pyramid where the base, so the base can just be any old splodge, but we're just going to make the base area equal to x/2. And then what we can do is we can cut both of these pyramids vertically. And we can realize that in each one, we just get a slice that is similar to the base. But the ratio of the area of the slice to the area of the base is the same, because it just is determined by how far down the pyramid that we've cut. So the area of any slice of the slice at any height have got the same areas. But now this irregular pyramid, we know its volume. It's the same volume as the square base pyramid, but the square base pyramid has got volume 1/3 x squared times the height, but x squared is just chosen to give the same base area. So the volume of both of these pyramids is 1/3 AH. So what we've got here is we've gone from one special pyramid where we've known its volume, which is the square base pyramid that you get from cutting a cube. We've then manipulated it to turn it into any pyramid in such a way that they've got the same, that the volume satisfies the same formula. Okay, and because a cone is just a special case of a pyramid, the volume of a cone is now justified. Okay, little thought experiment now. And I hope you like this observation. What is the what can anyone describe? So this is a bit more algebraic. Okay. Can anyone describe this shape and what is the volume? So this is the set of points in the plane where 0 is less than or equal to x, x is less than or equal to y is less than or equal to z, and z is less than or equal to 1. Okay, so because all the coordinates are between 0 and 1, it's clearly a subset. It's clearly a subset of the cube. Okay. X is less than or equal to y. So the distance into the board is always greater than or equal to the distance to the right. So the line x, it's probably worthwhile drawing the line x equals y. Okay, so the line x equals y is like this, and then y is bigger than x is this side of that line. We can then do a similar thing. The line where y equals z is where the height is equal to the depth into the board. So those are lines like that. And we're above that line. Okay, so what we end up with is we end up that we are a sort of right tetrahedron whose base is this, and then it goes down as a pyramid to a point which is 0, 0. Okay, so this is a pyramid. Okay, and the base area is 1 times 1 over 2 because it's a triangle. So the base area is a half. And then the height is 1. So the volume is 1/6. But can anyone give a kind of counting reason why this volume is 1/6? So notice that we had this shape is a pyramid, a triangular base pyramid. But notice that the way I define this shape is just one order of x, y, and z. It's x, y, and z increasing. But I could write down different orders of x, y, and z. But by symmetry, they're all going to have the same volume. Now, how many orders are there? well, how many permutations are there of X, Y, and Z? Or how many orders of X, Y, and Z? I mean, an order of X, Y, and Z is just a permutation. Yeah, because a permutation like X, Z, Y makes can make a can correspond to an ordering. So the number of permutations is 3 factorial. So clearly, the volume of this special tetrahedron is 1 over 3 factorial. Okay. And notice that the area of the base, well, it's just the ordering of 2 of the variables, so it's a half. And then the third came in when we got the volume formula for the pyramid. Now, this is where you just need a little bit of a flight of imagination. If there were more dimensions, okay, so if we had the shape which was 0 is less than W is less than X is less than Y is less than Z is less than 1. Now, I can't even begin to draw this, yeah? But what is clear is whatever notion there was of volume in 4 dimensions, this shape would have volume 1 over 4 factorial, so 1 over 24. Okay. Now, what would it consist of? Well, when Z was 1, that would correspond, in the 3-dimensional case, when Z was 1, we had a triangle, and then as Z decreased, everything just went down to a pyramid. Here, when Z is 1, we've got a pyramid, and then everything's going down to a point. So we've got like a 4-dimensional pyramid. Okay. Now, by a sort of 4-dimensional version of Cavalieri, what's the volume of a 4-dimensional pyramid going to be? Well, it's going to be base volume times height by times some factor. Well, the base volume is just the volume of my pyramid, which is 1/6. The height is 1, and the factor that I need out the front to make everything correct is 1/4. So for a 4-dimensional pyramid, the formula for the volume is 1/4 base volume times height. For 3 dimensions, it's 1/3 base area times height. And then for 2 dimensions, the area is 1/2 base length times height. And I really like this example. It's a little bit high tech and it's not classical geometry, but I quite like this example because what it does is it shows that the formula half base times height, which is the formula for the area of a triangle, is the 2-dimensional version of the base. The volume of a pyramid is 1/3 base area times height. And in general, the factor that you're getting at the front, which was a half and then a third, is 1 over the dimension. So that gives a sort of generalized notion of the volume of an n-dimensional analog of triangle, then pyramid, and so on. Okay, just thought you'd like that. Does anyone have any questions about that? Or are people happy for me to continue? And I haven't taken any requests. If people are happy for me to continue, put a thumbs up and maybe just a kind of request. We've got about 15 minutes, so we've probably got time to do one more question on the sheet. So just a request for any question that they thought looked particularly interesting. So far, I've only got one thumbs up. Who else is? Oh, there's only 3 of us. Okay, whoever gets in fastest finger first, whoever gets in with a request, just look at the sheet, pick a problem. I don't know, pick one that looks hard. Maybe the optional problems. Oh, okay, right. Just before we go on to the optional problems, there is one thing which I want. So have a look at the optional problems while I'm just doing this next little bit, and then pick the one which looked best, and then I'll try and go through that one in the time. But before I do that, I just want to look at this comment on the sheet where it says the surface area of the radius r is 4 pi r squared. And then it says there are many ways to obtain this result. Okay, and then it gives a suggestion. I can give a much simpler way of obtaining this result than the one which they gave. Can anybody else think of a simpler way of going from volume of a sphere is 4/3 pi r cubed to surface area of a sphere is 4 pi r squared? Just stare at the two. What mathematical operation takes you from 4/3 pi r cubed to 4 pi r squared? Differentiation. So we're going to take a vote in the chat, right? Who thinks that that is coincidence? Who thinks that it's a coincidence that if you differentiate the volume, you get the surface area? And who thinks it's kind of emblematic of something? Well, let's imagine we've got a sphere. Of radius r. And then let's make the sphere that little bit bigger. So let's make a sphere of radius r plus delta r. Well, what's the increase of volume? So the increase of volume is this little shell. Okay, but now let's imagine this shell. Okay. This shell, if we cut it and flattened it, now it's another story that you can't take a sphere and make it flat. But if you could, its thickness would be delta r, and its area would be the surface area of the sphere. So the change in volume is the change in the surface area of the sphere multiplied by delta r. So dv over dr, and it's only approximately equal to a, because actually the thickness, you can't quite turn it into a sort of flat chip. But if you make r smaller, you get a better and better approximation. So dv by dr is equal to a. So what you could do is just differentiate the volume of a sphere to get the surface area. You get exactly the same thing, and I always teach it like this actually. If you think of a circle, if you think of the area of a circle, think back to kind of primary school when you started doing pottery and they used to make you do coil pots. So if you make a kind of coil pot with like a coil of clay, this coil of clay, which is your new area, is your circumference. multiplied by the change in your radius. But obviously it's a little bit out, because if you made a rectangle, the edges wouldn't quite join at the end. But nevertheless, you get that dA by dr, to a good approximation, is the circumference. And as you make dr smaller, the differentiation becomes precise. Okay. And so the area of a sphere is pi r squared. And if you differentiate it, you get 2 pi r, which, surprise, surprise, is the circumference. Okay, let's have a look at the chat and see which. Yeah, would this extend to n-dimensional spheres? Yeah, absolutely, it does. The volume of an n-dimensional sphere is a nice exercise. Okay, no one's suggested anything in the chat, so actually, I'm going to finish with arguably the best bit of classical geometry ever, and I'll tell you the name of this theorem later, but this has just popped into my head as a great thing to do. And this is an alternative derivation of the surface area of a sphere, and I think you might just like this. Okay, so what I'm going to do is I'm going to draw a sphere, and I'm going to draw the sphere inside a cylinder of the same radius. Then what I'm going to consider is I'm going to consider a vertical slice of height, I'll call it delta h. Okay, so that's going to be my height upwards. This angle here is going to be theta. And what I'm going to do now is I'm going to consider the area of this ring. The way that this question is often formulated is, imagine a hemispherical loaf of bread, and then taking a slice and asking how much crust is there, okay, at that height. Now, there's two factors at play. The higher up you slice, the smaller the circle of bread that you get. But on the other hand, the higher up you slice, the crustier it is. Because if you take a slice at the North Pole of the bread, you're almost all crust. So let's see how these two factors kind of interact with one another. So we've got a slice of height h. This angle is theta. The crust is like at 90 degrees, is like tangent to the circle, so it's at 90 degrees to the radius. So this angle is 90. This angle here is 90 minus theta. So this angle in here is theta. So if you think of this triangle here, this is the height, this is the length of crust, this is theta. So the length of crust times cos theta is equal to, the thickness of the slice, I'll call it delta h. So that's the length of the crust. That length of crust is then stretched out around a circle whose circumference is the radius of the circle at that edge. So the area of the slice of crust is L times 2 pi little r. Okay, but little r is big R over cos theta. But then L is delta H times, sorry, little r is big R cos theta. And then L is delta H over cos theta. The cos thetas cancel. So we get that the area of the crust is 2 pi r delta H. But wait a minute, that's interesting, because if we project out to the cylinder, 2 pi r delta H is exactly the same as if I just take that vertical slice and stretch it round the circumference of the cylinder, which is 2 pi r. So the slice of bread at around the cylinder is 2 pi r delta H. So this is now a very nice result, because what it shows is that if you take a slice of bread of a certain thickness, it will have exactly the same amount of crust at the equator as it does at the North Pole. Because at the equator, you've got a big circle, but the crust is vertical, so you don't have that much crust. As the crust bends inwards, that effect counteracts the fact that the circle is getting smaller, so you get the same amount of crust. But crucially, I mean, this is just a bit like Cavalieri's principle for area, the area of each slice is the same. So what we've got is that the surface area of the hemisphere is the same as the area of the cylinder. But the area of the cylinder is just 2 pi r, which is the circumference, times its height, which is r, so is 2 pi r squared. And then if you double up, you get the surface area of a sphere is equal to 4 pi r squared. If there's any geographers in here, you get a nice result that if you take a sphere like the Earth, if you were to consider putting that sphere inside a cylinder of the same radius, then if you just project outwards onto the cylinder, then the area is the same. Okay. And what's going on there is, if you picture a landmass like Antarctica at the North Pole, okay, it doesn't take up much height on the cylinder because of the curvature of the Earth, but it's also disproportionately stretched. So the radius becomes really long. So what this gives you is so it's distorting in terms of shape. So it gives you a projection of the globe on, you can make a map of the globe where the area is the same, but shapes are distorted. And that's a really cool bit of 3D geometry. If you ever go on holiday to Sicily, you can see the tomb of the mathematician Archimedes, and of all his very many geometric theorems, this is the one he considered the best. And so there's an engraving of this diagram on his tombstone. And so this result is the Archimedes tombstone theorem. So I think that's a suitably nice way to finish. So if you're happy with that example, put thumbs up in the chat. If you've got any questions about the Archimedes tombstone theorem, let me know. If you've got any other comments, let me know. Otherwise, I will finish the webinar soon. So in the chat, we've got thumbs up. It's good. Yeah, so I think that's a really nice bit of mathematics to finish on the tombstone theorem. Can I send the OneNote page? I find OneNote is a really good program at everything apart from sharing stuff. So I'm going to do Microsoft Print to PDF. There we go. I've done that. Any other final comment? And I'll send that to Vlad and he can pass that on to you. Any other final comments? Excellent. Okay, we'll finish there. I think this is the last webinar of 2023, so I hope you enjoyed that. And I look forward to seeing you again in 2024. Oh, good. Someone said in the chat that it was fun. That's always nice to hear. If you're still finding maths fun on a late, dark evening in December, then you've got your priorities right. Excellent. Okay, have a lovely evening, everybody. Yeah, and it was interesting methods. I did try to put a different, partly because I'm not naturally good at geometry. I just tried to do a few things which were maybe sort of vector-based or kind of a little bit more. I love that counting argument of why the higher dimensional pyramid has got volume 1/n factorial. Good. Anyway, yeah. Merry Christmas to all of you too, and I'll see you in the new year. So bye-bye, everybody.